Okay, stats kids. This is section 4.2, and I'm going to warn you ahead of time that this might be a little bit longer of a video just because this section is what we're going to do over the course of a couple days. So you don't have to watch this video all at once. If you want to start and stop it, that's totally fine too. This assignment should be posted online, so you can work at that at any point in time. And a lot of the stuff that is in this section should feel kind of similar to, should feel, I don't know, like you've done this already, okay? Because we've done this in algebra, we've done this in geometry. This is all probability, and it's the addition rule and the multiplication rule, okay? So I'm just going to review some things that we know about addition and multiplication, because addition is the or section, multiplication is the and section. So that's how you know when you add or when you multiply, is that you will see kind of those keywords or and and. Also, in an or statement, you're only choosing one thing, but you might have multiple categories that you're choosing from. Like I want to come in and choose a boy or a sophomore, I'm only choosing one person, but I am choosing from multiple categories. The word and, you are choosing more than one thing. Choosing more than one thing. So maybe I'm pulling two cards, or I'm choosing two people, or I'm flipping two coins, that type of thing. So those are ands and those are ors, and only one thing or choosing more than one thing. So addition rule for these are the or statements. You're only choosing one. What you have to be careful of for the addition rule is whether you have stuff that is called, I'm going to skip down here to mutually exclusive events. Mutually exclusive, and they use a different word for mutually exclusive that we've never used before, and they call it disjoint. So if you see that word, that just means mutually exclusive, okay? Or we have things that are inclusive, okay? Mutually exclusive or inclusive, they call them disjoint and not disjoint, okay? And I'm going to show you kind of what mutually exclusive is and inclusive is. So mutually exclusive would be like a freshman or a senior, okay? You cannot be in both categories, versus, let's say, a sophomore or a volleyball player, right? You can be in both categories. So that is inclusive versus you can't be a freshman and a senior at the same time for mutually exclusive. Okay, so those are the things that we have to worry about. And let me go back up to the formula here for this. So we have that when we're trying to find the probability of A or B, like that sophomore or football player, we take the probability of a sophomore, the probability of a football player, but then we subtract out the people that are in both categories. Okay, and the reason why we do that, we'll see here in just a second, is that we don't want to, the people that we had in as a sophomore were here, the people we have as football players are here, but some of those people are overlapped, so we don't want to count them twice, all right? So let's see that example down below here. Drug testing of job applicants, we have this contingency table, or this two-way frequency table. This is a two-way frequency table, and the things that we have going on is using drugs, not using drugs, positive test, negative test, okay? So what should happen is, if you are using drugs, you should test positive for drugs. That's happening. 45 people that were tested positive, and those were the people that were actually using drugs. What should not happen is you should not get a positive test result if you're not using drugs. That would be like something weird that's happening in the test, like, I don't know, poppy seeds will set off a breathalyzer or whatever, those type of things, okay? Another false negative or another false result is you should not get a negative result if you're using drugs. These are the people that are lucky because they're using drugs, but they're testing negative, so they're somehow cheating the system. These are the unlucky people. Okay, but then 480 should is a true result, you should test negative if you're not using drugs. So that type of thing is happening, okay? And what's the question that we have going on here is it says if one subject, again, there's the word one, we're only choosing one thing, is randomly selected from the 555 subjects shown. I'm going to put 555 down here. Given a drug test, find the probability of selecting a subject who had a positive test result or uses drugs. Okay, positive or uses drugs. Okay, so I'm going to erase some of this stuff over here. And let's figure out our totals before we do this, okay? So we need to know how many total people were positive. So 45 plus 25 is 70. How many people were total negative was 485. How many people total used drugs? If you add these two together, that's 50. And how many people don't use would be 480 plus 25, so like 505, I think, something like that. Yep, 505. Okay, so what is the probability of having a positive test or them being a drug user? So we want positive or use, okay? And the chances of them, or the probability of them being positive was 70 out of a total of 555, okay? So I'm looking at these guys. Versus, or means we're going to add. The drug users were these guys, and that is 50 out of 555. But you will notice that when we add those together, the 70 and the 50, these 45 people that are stuck in the middle were counted in this number and in this number, okay? So we have to subtract those 45 out of the 555, and we will end up getting an accurate answer. I'm going to do this. I'm going to take 50 minus 45, and that's 5. So 5 plus 70 is 75 out of 555. Okay, and that's whatever that decimal ends up being. You can either leave it like this or convert it to a decimal. Really, we probably should have reduced that, but I'm just going to leave it there like that. Okay, we've already talked about disjoint or mutually exclusive, but let's do some examples here. So they say event A and event B. They say randomly selecting someone for a clinical trial who is male and randomly selecting someone who is female. They say you can't be both, so that's why those two things are exclusive. The person cannot be both, okay? The next one is randomly selecting someone who is taking a statistics course and someone who's female. So a stats student and a female, you can be both a female and in stats at the same time. That is legal. That's inclusive, okay? Summary of key points of addition, you will see the words or, and you will add the number of ways A can occur, the number of B's can occur, but be careful to add without doubling content or double counting. So I'm going to put you may need to subtract the people out of the middle. Okay. Now, if they are exclusive, meaning you don't have anybody in the middle, you have nobody to subtract out. So you would just add those two things together and be done with it. Okay. But if you have people in the middle like inclusive, these would be, you would be needing to subtract them. Subtract these. Okay? All right, let's go down and see what else we've got. All right, so then they have something called complementary events, okay? And so let's say A is the event down here, they say, of having a sleepwalker. So A equals the sleepwalkers. Okay? Then the complement of that would be not a sleepwalker. Okay? Okay, but they denote that as, I want you to really pay attention to this notation because I know you have a question on it. They denote that as A bar, okay? A bar is a complement. So if A is the original event, the opposite of that is not a sleepwalker, that is A bar, okay? Based on the journal article, the probability of randomly selecting a person who sleepwalks is about 29%, okay? So that's probability sleepwalked equals 29% based on the data from whatever, okay? If a person is randomly selected, find the probability of getting someone who has not sleepwalked. So they're saying, what is the probability of A bar, which equals the probability of no sleepwalk? Okay, and this notation is what you'll use. If the probability of yes sleepwalking is about 29%, then the probability of no sleepwalking would be about 708, I think, is what it is. Yes. So no sleepwalkers, about 70.8% is what that will look like. So that is called a complement. Complement. because those two things complement each other, because this guy and this guy should always add up to be 100%. That's why they complement each other. They work together to make up that full 100%. Okay? All right, multiplication rule. Down here, this is multiplication. We talked about it at the beginning. These are the and statements. These are the more than one things happening. More than one. Okay? And the thing that you have to worry about, like up here with addition, we had to worry about whether they were exclusive or inclusive. Here you have to worry about whether they are independent events or dependent events. Independent means they're not related. Not related. And a lot of times you will see the words with replace. Okay, with replace on independent events. Okay, so if you're drawing a card, the first time you draw the card, you're out of 52 cards, and if I replace it, I still have 52 cards when I draw the second card. So those two things are independent of one another, because it doesn't matter what card I drew here, I still have 52 cards in there that I could draw the second time. Dependent events. I'm going to say the second event depends on the first. And you will always see the words without replace. Without replace here, okay? And the reason why I say the second event depends on the first event, let's say I'm drawing out of 52 cards the first time, and I drew the ace of hearts, okay? I drew the ace of hearts. What that means is if I don't replace, I have 51 cards the second time, and there's no way that I can draw the ace of hearts. So can't draw ace of hearts. There's no way that I could draw that. So that's why this draw depends upon what I drew over here, because the ace of hearts is now not accessible to me. Okay, let's go down to this example. They've taken that contingency table or that two-way frequency table from above, and they've just done the positive test and the negative test results for the people who use drugs. So we have the 45, 5, and 50. And they're going to ask us some questions about this. So if two of these subjects who use drugs randomly are selected with replacement, underline that word, with replacement, find the probability that the first person selected has a positive test result. So I'm going to do down here, I'm going to go part A. We want the first person to be a positive and the second person to be a negative, okay? So I kind of just use this little visual aid to know like what I'm doing each time. So I'm going to do my fraction here times another fraction, okay? The fact that I'm drawing two people means I'm going to be multiplying, okay? The chances of that first person being positive is 45 out of 50. The chances of that second person being negative is 5 out of 50 because I am replacing. With replacement means the second time I do have 50 still in my sample here, okay? Then I'm going to go ahead and reduce. So 45 out of 50 is 9 over 10, and 5 out of 50 is 1 over 10. And I don't think anything else will reduce, so I just take 9 times 1, which is 9, and 10 times 10, which is 100. And if I convert that to a decimal, 9 over 100 is 9%. Not a decimal, a percentage, 9%, okay? Part B is saying do the same thing, but do it without replacement, okay? So we wanted to have a positive person first and a negative person second, okay? So my first chances are not going to change. That's still going to be 45 out of 50, okay? But the second time around, I am going to subtract 1 because I'm not replacing, and this person is still taken out of the picture. So I only have 49 people left over. Now, you assume that when you're drawing this person here, you're assuming that the person that you were looking for was in fact what you got. And what I mean by that is this, that if I'm trying to get a person with a positive test, I'm assuming that I did in fact draw a person with a positive test. So there are still 5 people remaining that are negative, okay? I don't assume that I drew a negative 1 here and there's only 4 here, okay? I only subtract from the bottom number and not the top number. Now, there is a time where, let me finish answering this question and then we'll talk about that, okay? So 45 out of 50 is 9 out of 10, and 5 out of 49 I don't think reduces, but I can reduce this 5 and this 10 to be 1 and 2. So 9 times 1 is 9, and 2 times 49 is 98. So 9 out of 98, which is slightly less than 9%, okay? Or no, slightly more than 9% actually. So that's kind of how that works, okay? Now, there is a situation where you will subtract 1 from the top number, and that would be if you were getting, like, let's say 2 positive people in a row. The first time positive would be 45 out of 50. The second time positive, you would have 49 in the bottom, but this would be 44 instead of 45, okay? So that's the only time that you will end up subtracting from both the top and the bottom number, is when you're looking for 2 of the same. And that's kind of how that works, okay? Let's move on down here and let's talk about when we're having independent events, or excuse me, when we're having dependent events, you subtract from the bottom number. Subtract from bottom number, okay? But this is treating independent events as though they are independent. So they're saying even though we should subtract from the bottom number, we're not going to. We're not going to, and I'm going to show you why. Okay, so this is called cumbersome calculations. Okay, when you have really, really, really big samples like this down below here, okay, we're not going to subtract from the bottom number even though we're supposed to. So let me show you why that is. Okay, example 5, drug screening and the 5% guideline for cumbersome calculations. All right, assume that 3 adults are randomly selected without replacement. This is when we should subtract, okay? Because without replacement, we should subtract from that bottom number, okay? Now, we are surveying 247,436, 800, whatever, all of those. That's a ton, 247 million, okay? Also assume that 10% of adults use drugs. So I'm going to say 10% equals users. Okay, find the probability that the 3 selected adults are all drug users, okay? So rather than using this really big number, I'm going to use 10%, okay? So I'm going to take, and I'm trying to find that 3 selected adults are all users. So this is going to be a use, and the second person is going to be a use, and the third person is going to be a use, and I'm going to multiply those guys together, okay? Now, what I'm going to do is I'm going to look at use, all of those, and 10%. So the chances of the first person using is 10%, which is 10 out of 100 as a fraction. 10%, 10 out of 100, or 1 out of 10, right? Okay. And when it's without replacement, what I should do is this now should become 9 out of 99, right? And this should become 8 out of 98. Okay, but we are doing 247 million people. So if I'm really, what I'm doing is I'm subtracting 1 from this number, right? So if I'm subtracting 1 from that number, 247, 436, 829 is now my new bottom number. And what's happening is if I subtract 1 from this bottom number, I'm still going to have like really, 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 really close to 10% users, right? Okay, so this 10%, because it's a percentage, we're not going to subtract, and because this number is so large, because even if I subtract 1 from the bottom number, it's going to be so close to 10%, it's going to round up to 10% anyway. So I'm going to leave it as 10% rather than subtracting, and that's the reason why we don't subtract from the bottom number. We still use 10 over 100, and 10 over 100 is, even though we should subtract, we're not going to because we have such a large number. Okay, so I hope that kind of made sense. If I subtract 1 from this number, it will still end up being basically 10%. Okay, now I wrote these guys as fractions each time, but what you can really do is you can still leave it as 10% or make it a decimal instead. So 10% is 0.1 times 0.1 times 0.1, which is going to be 0.001. I just moved the decimal 3 places. And that's the probability of getting 3 adults all in a row that use drugs, okay? So that's kind of how that works. And that's for, they call it the 5% guideline for cumbersome calculations because we're selecting 3 people out of this 247 million. So 3 out of 247 million, I'll do, this equals less than 5%, right? So I'm choosing 3 out of that many. That is less than 5% that I'm choosing. So I am allowed to not subtract even though I should, okay? So that's kind of how that works with the less than 5% rule, okay? All right, a couple more examples. Holy cow, we're trucking right along. Birthdays. When two different people are randomly selected from those in your class, find the indicated probability by assuming that birthdays occur on the same days of the week. Okay, we're not talking about days of the year. We're talking about days of the week with equal frequencies, okay? So find the probability that the two people are born on the same day of the week, okay? Now, I'm going to do part A over here. I'm going to do part B over here. Okay, so part A, two people born on the same day of the week. It doesn't matter what day they are, just as long as it's the same day. So I could have 2 Mondays, I could have 2 Tuesdays, I could have 2 Wednesdays, I could have 2 Thursdays, etc. Right? Okay, so let's talk about our first person and our second person. Okay, our first person could be born on any of the 7 days of the week. So he has a 7 out of 7. He can choose whatever day he wants, okay? But this second person has to match the day that he's on, right? So let's say this first person was born on a Wednesday, okay? The chances of the second person being born on a Wednesday is 1 out of 7, okay? And that's true for a Thursday or a Friday or any other day of the week, right? This first person gets to choose what day they are, and then the second person has to follow that. And they have a 1 out of 7 chance of matching that, okay? 7 out of 7 times 1 out of 7, you can reduce this 7 out of 7 to be 1 over 1. So I just have a 1 out of 7 chance of my first and my second person matching the day of the week that they were born on, okay? But part B says find the chances that they both were born on Monday. So now that changes things a little bit because, let's say first, I don't know why I said day. First, second, okay? The chances of my first person being born on a Monday was 1 out of 7. The chances of my second person being born on a Monday is also 1 out of 7, okay? So there's a 1 out of 49 chance that they are both born on Mondays, okay? So that's how it changes a little bit. Same day of the week versus both being born on Mondays, okay? All right, if you need to pause this video or come back to it, I'm getting long-winded here, but I'm just trying to roll this out for the people who are going to FFA, okay? So, moving on, example 7. How much do we have left here? Oh, we're almost done. Okay, all right. So example 7. Okay, redundancy for better safety. Modern aircraft are now highly reliable, and one design feature contributing to the reliability is their use of redundancy. I am so glad that they do this, whereby critical components are duplicated so that if one fails, another one will work. So this is like the benefit of putting multiple engines on an airplane, and those, like maybe there's 3 engines on an airplane and you only ever use one of them. Well, those 2 other ones are there just in case the first one would fail, right? You have a second one, and if that second one fails on accident, then you have a third one. So that just decreases the chances of the plane going down for any reason, okay? So, for example, the Airbus 310 twin-engine airliner has 3 hydraulic systems. I'm going to underline that. So that if any one of them fails, full flight control is maintained with another functioning system. And they put 3 of them on there in case the first and the second would fail, okay? So for this example, we'll assume that the probability of it failing is 0.002. That is still less than 1%. If we convert that to a percentage, that's 0.2%, okay? So it still has a less than 1% chance of failing, but actually, this number makes me a little bit worried because 2.2, this means that 2 out of every 1,000 planes that are in the air have a system failure, right? This is 2 out of 1,000, okay? And there are thousands of planes overhead right now. So if 2 out of every 1,000 are failing, that's actually kind of a significant number, even though it's less than 1%. It's still 2 out of 1,000, okay? So that's why they install more than one system, okay? If the Airbus 310 were to have one hydraulic system, what is the probability that the aircraft's flight control will work for the flight, okay? So if it has a 0.02 failure rate, this is kind of like doing the complement of that, okay? The complement is it working, right? Which would be subtracting that number from 1. So we're going to take 1 minus 0.002, which is 99.8 or 0.998, which is a 99.8% chance that it is going to be just fine and nothing bad is going to happen, okay? 99.8% of the time, it's going to be just fine, okay? Given that the Airbus 310 actually has 3 independent hydraulic systems, what is the probability that on a typical flight control will be maintained with a working hydraulic system, okay? So here's the deal. We want to know that all 3 of them are going to be working, all right? So the chances, so I want the first one to work, the second one to work, and the third one to work. Okay, so work, work, work. It has a 0.998% or 0.998 probability of the first one working. The probability of the second one working is also 0.998, and the probability of the third one working is 0.998. And again, we don't have to subtract from those numbers because we're talking about like tons and tons and tons of systems here, so we don't have to treat those as dependent. We don't have to subtract from those numbers. We can just use those percentages the way that they are. And if we multiply those together, this is as though we are taking 0.998 to the third power, if you don't want to multiply them together like that. And 0.998 to the third power is, wait a second. Control will be maintained with a hydraulic working system. Has 3 independent, blah, 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 blah. Poop. Hold on. We got to do something. We got to do something different. I'm going to erase. You're going to hate me. You're going to hate me. You're going to hate me. I'm going to erase. We did something different. We did something weird. We don't want to look at all three of them working at the same time, because if the first one is working, we wouldn't even take into consideration the second one working, right? Because we don't care about the second one if the first one is working. So what we need to look at is over here, we're looking at fail, 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 okay? Sorry, you're going to kill me. I'm sorry. We're looking at fail, fail, fail. So the chances of the first one failing is 0.002. Chances of the second one failing is 0.002. Chances of the third one failing is 0.002. Let's do it that way. Yeah, because if we were doing work, 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 we wouldn't even care about the third one working if the first one's working, or the second one working if the first one's working. So this is what we're going to do. We're going to do 0.02 to the 0.002 to the third power is what we're going to do. Okay, 0.002 to the third power. Okay, and that is 8 times 10 to the negative 9th power, which is 0.000000008. It's 8 with 8 zeros in front of it, okay? And this is the chances that all three are going to fail. That is the chances that all three systems are going to fail. So the chances that at least one system is going to work is the opposite of that. We would take 1 minus this number, and that is going to be 0.999999999. That's 8 zeros with a 2. So that is significantly increased from the 99.8% chance of it being successful before. This is 99.9999992. Okay, so 99 with 6 zeros, 2%, which is a lot higher percentage really than 99.8%. Okay, I would much rather be on a plane if this is the success rate than this one, even though it's only like 0.1 decimal, really 2 decimals off. Whatever. I would rather be on the 99.9999999% plane. So that's why they put that redundancy in there. For better safety, they put more than one system on there, okay? All right, moving on. Last thing, the rationale for the multiplication rule. To see the reasoning that underlies the multiplication rule, let's consider this pop quiz. You guys might have talked about this in Algebra 2. I know we did. And we called this the fundamental counting principle. Fundamental counting principle. Okay? Fundamental counting principle. And that just means take the number of options times each other to figure out how many total options that you could do. So options times each other. That's the fundamental counting principle. I'll show you what that means here in a second. So the first question that we have on this quiz is true or false. Okay? And if I have a true or false question, there's 2 options. Okay? If on number 2, my question is, by a small sample, we may judge of the whole piece who said that. Was it Judge Judy, Judge Dredd, blah, 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 blah. And there's 5 options there, okay? So if I answer this quiz, I could have done true and then chosen A. I could have done true and then chosen B, true and C, true and D, true and E. Or I could have chosen false first and chosen false A, false B, false C, false D, false E, okay? And the reason why I get that is because I have 2 options for the true and false, 5 options for the for the multiple choice, which gives me 10 total options that I could have chosen just for those 2 questions, okay? And that's what the multiplication rule illustrates for us, okay? Last thing, summary for addition and multiplication. When you're doing addition, you use the word or, and when you are adding, you want to make sure that you're only counting once. I'm going to put in here also that you're only choosing one thing, but it could possibly be from multiple categories. Okay, multiplication rule, you will see the word and. You want to make sure that you are dealing with, or you're taking into consideration, the independent versus dependent. Okay, whether you're subtracting one from the bottom number or not. And you are doing multiplication when you are choosing 2 or more things. 2 or more things. Okay. Okay, I apologize for that being so long of a video. Hopefully you lasted this long. Yeah, there you go. This is section 4.2. The homework's posted online. There you go.